Afternoon, everyone. I am Stanley MAK. My supervisor is Chun. And today my topic is dynamic and kinetics in electrochemical luminescence. Let me have a brief introduction to our research first. Our group interested in photophysics and electrochemistry in both the energy and environmental applications. We do the photophysical and electrochemical methods to understand the materials' intrinsic properties and the device performance. My main research interest would be lighting on the dynamic interfacial interactions, material designs, as well as the application in electrochemical luminescence. I think most of you may not know what ECL was, and let me have a brief introduction on it first. This phenomenon has been illustrated in 1929, and is only a brief description on this event that a luminescence was occurred on the electrical surface in the industry. Then later in 1964, there's a very detailed record in doing the experiment and illustrating the first chemical equation in the first picture of the ECL. Give us a very good foundation for further research on this event. And in 1980, the first device was developed by N.J. Park. And the purpose of this device is used for light emitting. And the current application of ECL is focused on DNA, RNA hybridization assay, also the detection of cancer cell. The aims on this research are improving the selectivity and the sensitivity. And currently, there's a rising interest in doing the device using ECL technology. Why? The reason behind is it contains low cost and easy fabrication, so that many methodology can do it. And this is the principle and the mechanism behind the ECL. We apply the bias on the electrical surface to generate an anion and cation. And this cation and anion will probably be together and undergo the annihilation reaction and give the excited state molecule. The excited state molecule will then release the energy as light. So we have light throughout the whole electrochemical process. My research study is focused on the printing and satellite. So why I choose this kind of materials, because it has long life for fluorescence, and the structure is very flexible design, and it has nearly 100% fluorescent quantum efficiency. This is why it's widely adopted in the lighting emitting device or the organic solar cell device. And this is my research target, which is composed of valving, center, and phenolene side groups. And other 5 of them are the model compound to help me to illustrate the concept in my research. Firstly, we have done some photophysical characterization. For example, very simple way to understand the luminescent properties during the photoluminescence spectra. So in my compound, PDT shows multiple emission peaks in here. And we need to find out what is the peaks it corresponds to. We used the time-installed photoluminescence to identify those peaks. And clearly, I used the model compound as the reference, and the center peak will be contributed to the phenolene satellite. And the differences are the emissions at 400 nanometers is the fluorescence, because the lifetime of this emission peaks is like around nanoseconds regions. And the fluorescence peaks lying on the 600 nanometers are the fluorescence of the paraffin Stanley. We also did the experiments on the temperature-dependent time-resolved photoluminescence. Why we do this experiment is because we want to find the explanation on the thermally activated dilated fluorescence. When we use triple exponential function to extract the component from the decay curve. And the first component will be attributed by the chiplet external transfer from the P to P type state. And the second component is the relaxation or chiplet state, the P homophobe. And the final component will attribute to the dilated chiplet excited state of the paraffin homophobe. And the proportions, and we find this event because when we look at the proportion of the decay component, and there is a increasing trend in the first component and increasing trend in the second component while the temperature decreases, which means that at the high temperature, there's a large group of population of the chiplet state in the PDT chiplet state, while in a low temperature, there is a large group of chiplet state PDP excited state. At this point, we can see that there's a reverse chiplet exciton transfer from the lower chiplet energy state to the higher chiplet energy state. And also, the energy gap between these two chiplet states is less than 0.5 electron volt. So it's possible that at high temperature, the chiplet energy exciton can back transfer to the chiplet at the higher chiplet excited state of TDP. Apart from the time-resolved photoluminescence study, we also conduct the experiment on femtosecond transient absorption spectroscopy. We can see in here there's a two peaks, broad peak in this spectrum, and the first depleting ground state, the first band is attributed to the ground state depletions in the UV region, and in the visible absorption band, it is a inner system crossing. The time constant of the ISC is around 800 picoseconds, while the ground state depletion has a kinetic decay of 2.9 picoseconds, which means that in our molecule, this is highly favorable for inner system crossing before the ground state depletion. We also do the work on the cyclic rotametry to understand which component will lead to the reduction site or the oxidation site. We compare the cyclic rotametry chromatogram with the M1 and M2 model compound. So note that there is the phenolene group is the donor group because it has higher intention to lose the electron, and the acceptor and paraffin as the electron accepting group because it has higher affinity to release the electron. Apart from the cyclic rotametry, we want to know the heterogeneous electron transfer kinetics. Why is it important? Because the ECL intensity is based on the generation rate of the K ion and I ion, which means that higher electron transfer kinetics will lead to more generation of K ion and N ion, so we can get more emissions from it. And we do the cyclic rotametry at different scan rate in order to understand whether this system is diffusion under diffusion control. We use the Van-der-Waals equation to obtain the diffusion coefficients value. And then we also need to know the value of transfer coefficient from the double plot, from the cyclotron shipping slope. And we obtain the slope here, and we can plug in the value in these equations, and so that we can get the coefficient transfer coefficients. Apart from that, we also need to determine the critical scan rate. So we need to identify the low scan rate and high scan rate peaks, so that when the intercept of these two lines, high scan, low scan rates, will give us the critical scan rate. From this equation, by using the divider method, and we can obtain, previously we have the transfer coefficient, critical scan rate, and diffusion coefficient, and transfer coefficients, and after all, we can get the heterogeneous transfer kinetics rate. And this is the result of the transfer kinetics, and we found that there is a rapid electron transfer rate in the following reduction center, and much lower electron transfer rate in oxidation. We also do the experiment on the potential state chemistry. This potential state chemistry can give us the current response to understand whether the formation of Ki or Ni is stable or not. In here, we can see that at the reduction potential, there's only a few current response is given out, which means that the reduced species of the PDT species is not stable. And under the same potential housing, and we will get the transient ECL. In here, we can see that because the formation of anion is not stable, and we can see that there is a great division under the cathodic pulse. In the cathodic pulse, and we can get a very high ECL intensity. Another interesting feature of this compound is there is a 30 nanometer bullshift in the ECL while comparing to the photoluminescence. To explain this, we have found a lecture that they explain it's possible that transient satellite can undergo the aggregations, and while they can also form a T conformation under the chiplet solid state, which has the higher energy compared to the P conformation. Once it is excited, and they will stack together, and will forming a sheet on the electrode surface, and when they want to release the energy, due to the steric effect, they cannot go back to the panel state, and it will emit a higher energy, so that therefore we will have a reshift ECL while compared to the photoluminescence. To understand the whole whether this ECL system is under energy sufficiency or not, and we can compare the energy of the fluorescence with the particle ion annihilation energy. And in this analysis, we can simply convert the fluorescent energy into electron volts, and we can obtain the singular excess state energy. And in here, the entropy of the particle anion annihilations can be obtained by the subtractions of the reduction and the oxidation potential, and we can get the energy. And we can find that the entropy used in ion annihilation is much larger than single excess state energy. So this system is an energy efficient process, and it goes through the S road. And this is the overall summary of how my target compound goes throughout the E-cell process. We use the electrochemical method to excite the molecules, and we use the photophysical method to illustrate the charge transfer dynamic after the excitation. And once the molecule is excited by electrochemical method, it will undergo the intersystem crossing and it will release the energy at its final stage, triplet excited state. And both of the triplet state quantium phosphine and the triplet state quantium phosphine will also emit the phosphorescence. So it's a zero fluorescent emitter. Apart from the quantium excited, we are also interested in studying the emitter using the halide or stem materials. Our target analyze is the CS4PPBR6, which is a zero-dimension materials. We can see in here under the UV light irradiations, we can see that the zero-dimension materials have very intense emissions. And this is the brief characterization to prove that we have successfully synthesized this compound. We also do the heterogeneous electron transfer kinetics analysis, and we find that the diffusion duration and the rate constant is high in this complex, and therefore is very good for the application in E-cell. We have also do the experiments on the temperature-dependent time-resolved photoluminescence to understand the exciton dynamics. When the kinetic transfer of two molecules can be described by the Marcus theory, and this is the kinetic of the energy transfer equation. When we combine the rate constant of the decay component, and it will have the simplified equations underneath. We use this simplified equation to fit into the various part of the temperature-dependent photoluminescence, and we find that activation energy of our proposed compound is lower than its brother compound, and the electronic coupling is higher. That means that the zero-dimensional compound has higher exciton charge and charge recombination rate and give us more radiations. And in the E-cell study, we have also pulsed the potential on these materials, and we can see that the endolic pulse, which means it's much lower than the reduction pulse, and which means that the oxidized form of these zero-dimensional materials is less stable. And in summary, we can find that from the photophysical experiments, we can see the electronic coupling and activation energy to analyze the material performance. And also, we can use the diffusion duration and electron transfer kinetics to understand whether this is good or not in the electrochemical reactions. Thank you.